So welcome back. In this video, we will be discussing the second approach to solve the height of binary tree after subtree removal queries. So in the previous video, we discussed the Euler tool technique of tree flattening to solve each query in order of one time. So in this approach, we will be discussing the DP approach. So what we can do is we can compute the level and depth of each node. Along with that, we can compute for a particular level L, what is the first maximum depth and the second maximum depth for a particular level L. After we have computed these, let's see how we can get our answer. So if we have a tree of, let's say 1 is connected to 2, 3, 2 is connected to 4, 1 is connected to 5, 6, then 7. Given this tree, the depth of the particular tree or height of height of this tree is clearly 3. So let's say we are asked to remove node 2. First of all, we find what is the level and depth of this node. Say it is L and D. Now that we know that a node having a level L and depth D has been removed, let's find out whether this node was contributing to the height of the tree. How we can check is, we find out what is the first maximum depth at a level L. If it is, let's say, M1, and if this M1 is equal to depth, when let's understand when will 2 be contributing to the height of the tree. It might happen that this 3 is connected to 8 and 3 is connected and 8 is connected to 9, and in that case the path from 1 till 9 would be the height of the tree, and this means that 2 is contributing to the overall height of the tree. So how do we check if 2 is actually contributing to the height? By checking the first maximum and of level L and depth D of node 2. If these two are equal, that means 2 can be contributing. Notice how I say can be, not exactly, because it might happen that 1 is connected to some other node, and this also in turn has a height of 4. So here both this height and this path are the height, can contribute to the height of the tree. So if these first maximum and second and the depth of the query node, in our case it's in 2, if these two are equal, that means 2 can be contributing to the overall height of the tree. So we need to find the second maximum of this level L, second max. So the answer for the particular query would be second maximum plus level of that particular node minus 1, because second maximum also uses this height, this edge, so we do a minus 1. So yeah, this is the answer. I hope it's clear. Let's say let's take another example. In if we have 1, then 2, then 3, then 2 is connected to 4. In this case, height is 2, and we have let's say another, it's 5, then it's 6. In this case, the height of the tree is 2. If we are asked to remove 5, we check what is the level and depth of 5. We have computed it previously. Then we check what is the first maximum at level L. Let's say it is FM and the second maximum is SM. So if the first maximum is equal to the depth of 5, that means 5 can contribute to the overall height of the tree. We go to the second maximum. In our case, second maximum of at higher level L is also 2. Because the first maximum, if it is this, then second maximum can be this. So first maximum of level 1 is equal to 2, and second maximum is also 2. Of 1 is also 2. So it might happen that both first maximum and second maximum are equal. That means there are 2 branches for that node which go up to the same height. So the answer for this particular query would be level of 5 plus second maximum at level of 5 minus 1. So let's see the code. It will be far more clear. In this, first of all, we call the DFS. For each node, we store its level and the height and the depth. Depth is basically the height of each node, the same thing that we do to compute the height of a tree. Then for a particular level, we check if this node's depth is greater than the first maximum of at that particular level. If it is, then we update the first maximum and the second maximum respectively. If if the first maximum is greater than or equal to the depth of that node, then we check if second maximum is smaller or not. If it is, then we update the second maximum. Then for answering each query, we get the level of that node, and then we get the tree height. How do we get it? The same thing that like we discussed. It will be level plus, then we check whether first maximum at that level is equal to the depth of that node. If it is, then we go to the second maximum of that level. If it is not, then we can easily take the first maximum. So we take first maximum of that level minus 1. So, and then we push it back to the result array, and then finally we return the result array. So this overall time complexity will be big of n, because we first of all we pre-compute the level and depth and the first maximum and the second maximum. It does in big of n time, and for answering each query, it takes order of 1 time. But say we have q number of queries, so the overall time complexity will be big of n plus q. Hope it is clear. And if you have any doubts, you can leave it in the comment section. Thank you.